the long-term goal of my research is to create a more effective biocontrol-based IPM strategy for onion thrips and Western flower thrips. And in order to do that, we need to know what biocontrol tools aren't working. Believe it or not, these pictures came from a grower that was doing all the right things IPM-wise. They were using a tried and true thrips biocontrol program, and it had been working really well for Western flower thrips. But then something changed, and then they started taking heavy damage. At some point, their thrips population had changed from mostly Western flower thrips to a predominantly onion thrips population. There was almost 80% onion thrips in these hard-hit varieties. What they didn't know was what it was about their IPM program that was failing. And they've been using a very typical IPM program, which is often referred to as the standing army approach. Regular releases of predatory mites, weekly biopesticide sprays, and nematode applications are the core components, although there are, of course, other options and combinations, and then each grower might have a slightly different recipe. Because thrips IPM programs are multifaceted, it's not immediately obvious which component is the weak link here. So to figure out why this program was failing to control onion thrips, we have to examine each component one by one. Now, there are plenty of studies already that show that the bios that we use for Western flower thrips do work for onion thrips. But the thing that's missing is comparative head-to-head trials. So we actually don't have any way of knowing whether they work equally well or not. The experiments I conducted on the biocontrol agents and pesticides in my master's project were done in lab trials. On the face of it, lab trials might seem like a strange place to start since they're fundamentally unrealistic. But the real world is made up of like hundreds of different factors, so it's really hard to pin down exactly what is causing the effect that you're observing. So we need to start in the lab and look at each factor in isolation before jumping to greenhouse experiments or commercial trials. Lab trials also represent the best case scenario. If a product doesn't work in a situation when we can control as many variables as possible, then it's not likely to work in a more complex environment once climate, plant structure, and other organisms start interacting with the thing we're trying to test. And since no one has done these comparative trials before, I needed to start at the beginning of this process. So my first trial looked at predatory mites, which are arguably the star of any thrips IPM program. For this experiment, I wanted to find out if there was a difference in the predation rate of different mite species on Western flower thrips compared to onion thrips. In this trial, I tested Cucumeris, Swirsky, Degenerans, and Lamonicus. I put a single mite in a container with 8 thrips larvae and saw how many thrips the mite ate in 24 hours. And this was a no-choice trial, so each mite was only given a single thrip species at a time. Generally speaking, the mites I tested ate at least as many onion thrips as they did Western flower thrips. In Swirsky's case, they actually ate more onion thrips than Western flower thrips. When comparing the mites to each other, Swirsky ate 68% more onion thrips than Cucumeris did. So Swirsky might be a better option for onion thrips, but this has to be validated in a greenhouse trial first. I also ran the same kind of trial as a choice trial, in which I gave Cucumeris and Swirsky equal numbers of each thrip species. Typically, onion thrips and Western flower thrips are both found in the greenhouse together. So if mites do prefer Western flower thrips for some reason, then that could explain why they don't perform as well for onion thrips as my previous no-choice trials suggest that they ought to. But what I found was the complete opposite. Both mite species ate more onion thrips compared to Western flower thrips. So what this tells us is that predatory mites' preference are not what's causing biocontrol failures. I ran the same kinds of trials with Aureus insidiosus and found similar results. They ate more onion thrips in the no-choice trials and exhibited no preference between the two in the choice trial. So based on this information, Aureus should also control onion thrips at least as well as Western flower thrips. Now, anecdotally, I have seen Aureus be very effective for onion thrips and would really like to test them out in a greenhouse trial to see if they actually are a better option than mites. Next, I tested the efficacy of Bavaria bassiana. The product I used for this trial was Botanigard, and I tested 3 different rates. The label recommends a range of rates, so I used the high end and the low end, and I also tested a rate that was 10-fold lower than the label rate. And again, I found no difference between the thrips species, which indicates that onion thrips and western flower thrips are equally susceptible to Botanigard. And the last biocontrol agent that I looked at was entomopathogenic nematodes. Although Steinernema feltiae is the most often used species in greenhouses, both Steinernema carpocapsae and Heterorhabditis bacteriophora have been shown to infect thrips. I tested all 3 nematode species in a lab trial that used a commercial peat-based potting mix as the substrate. The nematodes were applied to the substrate after thrips began to pupate, and I assessed how many survived to adulthood after 6 days. There was no difference in mortality rates of the onion thrips and western flower thrips for all nematode species, with one notable exception, and that was Steinernema feltiae, which is the species most often used in the greenhouse. It actually performed quite poorly against western flower thrips. This mortality rate is lower than what is often reported for lab trials for feltiae and western flower thrips, and my suspicion is that this was due to the potting mix substrate that I used. A lot of research in the literature uses either they put the nematodes directly onto the thrips pupa, or they use really simple fine-grained substrate like sand. But previous research by my colleague Taro Saito used potting mix, and he also found that feltiae caused very low mortality in western flower thrips. I could go off on a tangent, but I won't because I don't have time. But aside from this little mystery, what the data does tell us, back to our original goal, is that nematodes should work at least as well for onion thrips as they do for western flower thrips. So if all of the bios are supposed to work for onion thrips as well as they do for western flower thrips, so why don't they actually work in practice? Well, the actual mechanism that is driving poor biocontrol outcomes could actually be behavioral, either on the part of the thrips or the biocontrol agents. The laboratory assays are conducted in a confined 2-dimensional space, which is very different from the complex architecture of a plant. And lab trials don't allow for some of the behaviors that might affect thrip survival, such as where they like to be in the plant or their ability to escape predators. We already know that western flower thrips and onion thrips have some differences in behavior. Research from Cornell University found that onion thrips and western flower thrips are more active at different times of the day. I had the opportunity to confirm this in the greenhouses at Vineland. Being active at different times of the day is most likely to affect the efficacy of pesticides that rely on direct contact, such as Botanigard. So if onion thrips are not active in the afternoon, and that is when growers are spraying, they might pick up fewer spores compared to western flower thrips. However, this difference in behavior is not likely to affect the efficacy of systemic or translaminar pesticides. Similarly, the location within the plant matters for predators as well. Research, also from Cornell University, demonstrated that Aphidoletes works better for green peach aphids compared to foxglove aphids. And it's not because they have an actual preference for green peach aphids. What it is that green peach aphids are found higher up in the plant canopy, which is where Aphidoletes spends more of its time. We've also seen that there's a location difference between western flower thrips and onion thrips. Western flower thrips feed very heavily on flowers, as you can see in this picture here, whereas onion thrips do not. If predators are also drawn to flowers, this means that they're going to encounter western flower thrips more often than onion thrips. And finally, predator avoidance might be playing a role. When approached by a predator, many animals will understandably attempt to get away, but they don't all do this at the same speed. Research from the University of Florida observed that although western flower thrips and Florida flower thrips spend equal amounts of time in the flowers, when they are approached by Aureus, Florida flower thrips escapes more quickly than Western flower thrips. And then as a result, Aureus ends up catching and eating a lot more Western flower thrips. Unfortunately, all of those things take more time to untangle than I could fit into a 2-year master's project. But luckily, we have received funding for a second master's project to continue this work. We're still searching for the next student. So if you or anyone you know is interested in pursuing a master's in this field, they should get in touch with Rose Bowdenhouse as soon as possible.